So this is my last lecture. What we're going to talk about today is mutable references. Along the way, I've been sort of dropping hints that, here's some machinery, step index logical relations. It works in all of these settings, and it scales to features like references. So today, what I want to do is, in the simplest possible setting, I want to show you what some of these complications are that arise when you have mutable references and you try to do logical relations for them. So what I'm doing is basically I'm going to consider simply type lambda calculus with ML-style mutable references, and I'll come back to that in a second. And then I want to set up basically what's I've put back up on the board, the basic setup that we had for proving type safety. Okay, so I'm switching back to a unary logical relation, and we're just going to try to prove type safety for mutable references. But this basically demands that the model get more complicated, and I want you to understand the exact details of how. And I think that once you understand this, you can really, most of the work is done in terms of, you can then take it and make it a binary logical relation and talk about equivalence. Okay. So, and I want to try to do this in the first hour or so, and we've already started pretty late, actually. So let's see how this goes. Then I want to spend about 20, maybe 25 minutes just telling you about all of the research out there, a little bit of history of the logical relations, work on step index logical relations that has happened in the last, let's say, 5 years or so. There's been a lot of work. And mostly I'll just be throwing pointers at you, and so you can go look up things if you're interested. Okay, so let's get started. So I have simply typed lambda calculus with booleans, functions, and references. I've thrown in a unit type just because it's sort of a standard thing to have, and I'll get to that in a second. Okay, now before I even walk through this calculus, when I say ML-style references, what I mean is we want, in our simply typed lambda calculus, now we want to have the ability to dynamically create cells in memory, right? So you're going to have dynamic allocation. We should be able to read out of the cells, obviously, and then we should be able to update them. Okay? So assignment. But when I say ML-style, what I mean is that in ML-style languages in Java, for instance, you only have so-called type-preserving updates, right? Once you create a cell in memory, you cannot update it with a value of a different type. Are people aware of this? Is this confusing? Completely obvious? Completely obvious? Okay, good. All right. And people know why ML and Java have only type-preserving updates? What's the issue? Why don't these languages allow you to manually free memory? Why isn't there free like we have in C? Aliasing. Xavier had to say it. Oops. Okay, maybe we should talk about it then. Okay, so let's take a very, very simple example. So here's a function f. Maybe I shouldn't write so much on that side. Okay, here's a function f. It takes two references, a ref an x, which is a ref of bool, and a y, which is a ref of bool. Okay? Now, in the body of this function, what I'm going to do is I'm going to allow free. Okay, so first I'm going to go ahead and free x, and then I'm going to read the contents of y. Okay? That's my function. But now suppose that I call this function passing in x and y both pointing to the same memory cell. There's a bunch of memory cells. X and y are both pointing to this one. So at the beginning when I call the function, x and y both point to that cell, and it's true. Then I go ahead and free x. So this is gone. And now I try to read out of y. Oops. Right? Basically, free acts like, there are certain assumptions about the types of these, and you have two aliases, and now you won't be able to prove type safety, basically. This is not type safe. And rightly so. Okay, so languages which allow you to free memory cells or allow you to write a value of a different type into a memory cell over the course of the program, those languages are said to have so-called strong updates. Strong updates are when you can change the type of a cell after it's been allocated. Weak updates or type-preserving updates are when you are not allowed to do that. And languages like ML and Java have this restriction because of the aliasing problem, because you cannot infer things like this, right? You can't always figure out that things are pointing to the same thing. Okay, and just to really drive this point home, I mean, you don't actually just have to free, right? At this point, if my language had strong updates, suppose that I decided to put 5. So I started out with true, and then I decided to write 5 into x. Now it has a 5. And now I want to read out the contents of y, and I'm assuming that y is a reference to a bool. So maybe I read out the contents and then say, then do if then else. Now that's a problem too, right? This no longer contains a Boolean. Okay, so free or a type changing update, a strong update, it's the same problem. Okay, so this is why ML and Java have this restriction that you can only do type preserving updates. And the issue of freeing memory, it gets sent, it's the job of the garbage collector. We assume that once you've allocated a location, it's always going to remain in the heap forever, containing values of that same type. Okay, so it's monotonicity sort of property. Okay, so let's talk about our language. So Booleans, functions, references. The ... over here means we have all of the expressions we had before for the simply typed lambda calculus, right? Abstraction, application, so on. True, false, if then else. I've added unit, which has unit expressions which have the unit type. Written 1. We have new, which allows you to dynamically allocate new cells in memory. And we have dereferencing, bang E, read out of a memory cell. And we have assignment, so write some value into some location. And we have locations. So what are our value forms now? It's going to be true and false for Booleans. It's going to be lambda for functions. We have unit values for unit. And what values do we have for ref types? What's the value form? Yeah. Oh. The location, right. Should I stick to purple for a little bit, perhaps? Okay. All right, and then we add evaluation context. We have all the ones that we had before, and now we're, again, just doing left to right evaluation order, call by value. So we evaluate in all of these positions, right? It's a standard thing. Okay, so now let's set up the reduction rules. So in this language, we can't just have an expression E stepping to an expression E prime, right? Because we're allocating memory. So we need a memory or a store or a heap, whatever you want to call this. I'm writing S for store, but people write M, people write H, people write big S, whatever. You're free to choose whatever you want to call it. Okay. And I might actually be switching terminology. Sometimes I say memory, sometimes I say store. But that's what I mean. Okay, so now we have to talk about the small step operational semantics has to talk about program configurations, right? One program configuration steps to another. So our program configuration is a store and an expression, and it steps to another store and an expression. We take all the reduction rules we had before, and we just sprinkle the S's around, but none of those rules change the store, right? Because they don't touch memory. And then here are our new interesting rules. How do we do allocation, dereferencing, and assignment? So let's just write these out. So I've evaluated my value that I want to put into, right, over here, that I want to put into the store. So how do I actually allocate a new location? Extend the store, so take S and add a new location L to the store, and L maps to V. And new will simply return the location. But here we need an important side condition that we have to pick an L that is not already in the domain of the initial store, S. Right? So we pick a fresh location and we add it to our store. When we want to read out of a location, that location better already be in the store, right? So L is in the domain of S, and basically, we want to go read out that value. So the store remains unchanged, and the value that we return will be the contents of the location L in the store. By the way, the store is just a mapping from locations to values. That's obvious to people, right? Everyone good? Okay. All right, assignment. What do we want to do? L better already be in the store, right? So L must be in the domain of S. We want to update it, so we're just going to say, in S, put our new value V at location L. So this Here, this is extension, but here, this is just update the contents of L. And for assignment, I'll return unit. You could also just return the location that you've just updated. Doesn't matter. OK, typing rules. If E has type tau, then nu of E is an expression of type ref tau. If E is a ref tau, then reading out of E gives you something of type tau. Assignment, E1 has to be a reference. E2 has to have the right type tau, because it's a type-preserving update, right? So these two types have to match. And then assignment is legal, and it returns, the type checks, and it returns unit. OK, so that's the basics. I'm leaving out recursive types. You could just add it without any changes. But let me ask a question before I go any further. Yesterday, someone said, hey, you just have recursive types in your language. How can you write non-terminating programs? So my question for you today is, Xavier is smiling, can we write non-terminating programs in this language? Yes? So I just have unit, bool, function, and ref. How many people are completely convinced that we can write non-terminating programs in this language? Benjamin's hand going up is like, gives people more confidence, perhaps. OK. So yes, we can write non-terminating programs in this language. And here's a very simple example. OK. This is called Landon's knot. I think it's from the 1960s, 67 or something, a paper of Peter Landon's, OK, where he showed that you could do this. So let's create a new memory cell. OK. X is going to be a new reference, and we're going to put a function of type unit arrow unit into this cell. Okay, so we want to initialize it with lambda z unit. We'll just make it the identity function. Clearly, that has type unit arrow unit, right? Okay, and then we'll say let f be a function that takes something of type unit. And then in the body of that function, we want to read out of this cell x and apply it to this input z. OK, so since this contains a unit arrow unit function, we're giving it a unit, so the body has type unit. So this whole function f has type unit arrow unit. Yeah? OK. And sorry. And then what we want to do is we want to say, let's do an assignment. We're going to take our function f, which is of the right type, unit arrow unit, and put it into this ref cell. And then, semicolon just means, semicolon. And then we're going to call f with unit. What does this function, what does this code do when we run it? OK, so we have a cell x that contains f. So we call f with unit. All right. So we jump over here, we call f with unit, right? So this disappears, we evaluate this body. So we go and fetch the function that is now stored in x, right? And what's the function that's now stored in f? Oh, it's in x, it's f, right? So basically, when we say fetch the contents of x, we are actually fetching this function itself. So we are, f is therefore calling itself right here and passing in unit. So it'll keep looping forever. Right?
Sometimes if you have references, then you implement recursion.
Precisely. That's precisely the point of this so-called Landon's knot. Okay? So, so just as an intuition, you have non-terminating programs here, just with just with mutable references. Okay. All right. So. Let's push this up. OK, what we're going to do next is basically edit this unary logical relation that we had for type safety for recursive types, even though I've left out recursive types from the board. But that basic structure, I want to show you how we would need to change it. OK, so I made this explicit yesterday when I was writing on the board over there. I said that the v taus that I've been defining so far what are they? I pointed out that they're really just functions from nat to these sets of closed values, right? So all I'm doing up here in the line is making this explicit for you one more time. Okay, I just want you to remember it. It's going to factor in today. So the way we had built our model of types, the way we had interpreted types until now for type safety, was, we could think of this whole set types as containing type interpretations, I for interpretations, that were functions from these nats to these sets of closed values. All right? And we required that these functions be, we required that these type interpretations be downward closed, right? So if a value belongs to a type for k steps, it belongs to it for less than k steps. And that's all this is saying, right? If a value is in this set for k steps, then it's in here for j steps. Okay? So this was the general, this basically describes the properties that we had for our type interpretations until now. Okay, so what we want to do now is define, we want to extend this with references. So the basic thing that we need to do is define an interpretation for ref tau and say when do values behave like they have type ref tau for k steps. So what are the values of type ref tau? Thank you. Okay. So when does a location behave like it has type ref tau? Just in English. Okay. Oh, there you are. I was like, where is that? All right. So when it's dereferenced, okay, so when if you have a location, then, yeah, let's think about the elim forms, right? So Lindsay's saying you want to be able to, when you read out of that location, you want to get a value of type tau, right? And we can look up there, right? When we read out of, the elim forms for references basically are reading and writing. So, okay, let's extend this so that we, well, how can we say that? Right now, we don't have enough information in our model, so to speak, right? To be able to say that when you read a value, when you read something out of location L, if we added a store to the way we interpret types, right? If we started to parameterize these things, so I'll leave the k right where it is, but let's add a store. It looks like we need to have a store in order to be able to say what Lindsay just said, right? In order to be able to say that L behaves like it has this type if the contents of L in the store behave like something of type tau, the type that we expect, for, and I have to put an S here now, and we could put k here or put k minus 1 here because reading out of the store will take 1 step, so I'll put k minus 1. Okay, so we could do that. So this says, if this were our definition, and it's not our final definition, if this were our definition, this says that a location has this type if whenever you read out of it, it contains something of type tau. Okay, so what about, we only want to allow type preserving updates though, right? So if this is my semantics of references, this tells me what will happen when I read, but how do I ensure that I do the right thing, the thing mandated by the assignment rule? How do I know that I do the right thing when I write into that cell? Yeah?
Some sort of typing restriction on the store?
You have to have some sort of typing restriction, right? So you... you could annotate locations with type information. Very good. Actually, I forgot to mention something. Let's back up for a second. Let's look at the typing rules up there, because this is very related. I added typing rules for new and ref and assignment. I didn't show you the typing rule for unit, because that was easy. But what else have I just added to my language? Expressions. What's the last thing? Location. And I don't have a location typing rule. Do I need one? Okay, so this is the point that I've been sort of trying to make, right? Though, if you're doing a proof using progress preservation, then yes, you do need a typing rule for locations because, you know, a location is an intermediate term. But if you think about the program that a programmer writes down, a programmer never writes down an explicit location, right? So if you think about if you think about programs that haven't started running yet, they don't contain any locations. Okay, so expressions that contain free locations are intermediate terms. They arise once you've started running the program. And I've been saying this stuff about, you know, we're doing proofs of type safety in this style where you don't need to type check intermediate terms. So that's why I've left out the location typing rule. If I did have a location typing rule, you know, for those of you familiar with the presentation in TAPL, I think Benjamin uses sigma. So the form of the judgments would have to change. In order to say that L has type ref tau, you need a store typing or a heap typing over here, sigma, that maps locations to their types, right? And here we basically then need to say that, that sigma L is tau, right? But then that's going to change the form of all of our typing judgments. We're going to have to carry around a sigma. By the way, I like to use psi for this, and as you saw, I just made a mistake and I wrote psi again, so I'm just going to switch to psi. To avoid having to repeatedly correct myself. Okay? So it's just a heap typing. All right. So we don't have this. But the intuition for what was psi keeping around? Psi was keeping around, when you do a progress preservation proof, psi is keeping track of the type that every location must contain. Once it's been allocated forever in the future, it must contain that type. Right? And that's kind of a type of information we're missing here. We want to be able, this model needs to be able to track what location, what type a location will contain forever in the future, right? Now, so what I'm going to do here is I'm just going to get rid of the store S here and instead put in a psi. But my psi is not a mapping from locations to syntactic types. Okay? It's going to be a mapping from locations to semantic types, which are these kinds of things, these type interpretations that we've been building. Okay? All right, so let's see how that affects things. So now, if I, and by the way, I erased the S here, if that's confusing to someone. I'm going to make changes to the rest of the model to make sure that wherever in the definitions we have to actually run something, we pick a store. We're going to pick a store that satisfies psi, and so everything will be okay. All right, so the store doesn't really need to be part of this part of the model. Okay, so how do I change this definition now? So now a location behaves like it has type ref tau if my heap typing or store typing says that it should have type ref tau. That should basically be the intuition, right? So let's see. So basically, psi of L something like that. Right, because I said that my psi is mapping locations to semantic types. Someone have a problem with what's on with this definition? Do we need to use a step indexing on the V? Right. So the definition as written, we're defining interpretations of types at step level K, but we seem to be using something bigger, right? And our primary induction is on K. So let's see. Right. And the way I should do this is we want to say psi of L. So psi of L is one of these i's, which is now not just going to take a nat. It's going to take a natural number for the step index, but it's also going to take a store typing, right? So we need to come back and edit this part of the definition. All right? But let's hold that thought for a second. And then we want to say that here you want to use essentially some sort of k minus 1 psi type of thing, right? And you want to say that that is equal to the interpretation of v tau, and again here we want a k minus 1 psi kind of thing. People with me or people getting lost? Okay, so here's the basic idea. I haven't formalized it yet. It's still not yet the final, or at least I haven't told you enough to make sense of what I've put up there. And yes, it's not the final definition. Okay, but it's very, very, very close. Here's what we're doing. Okay, so before, by the way, the things these models that we're building, the step indexing trick, these are essentially what are called Kripke models or possible worlds models. How many people are familiar with that term? Okay, very good. A lot of you. All right. So so Kripke models are normally built from modal logic, where there's this notion of saying that something is true, not always. So just by analogy, initially we started saying that V looks like it has type tau, but then we finessed this a little bit and started to say, oh, we can't. We don't want that notion. We want the notion of V behaving like type tau to be relative to the world that we are in. And that's where the term possible worlds comes in. So the world that we are in is in this model was being characterized by the number of steps that we have left to run. And now what we're doing is we are enriching our world. Now the world that we are in is described by how many steps we have left and what the shape of our heap is. Okay? So, so stay with me. All right. So basically now we're saying that values behave like they have some type relative to some world. The pair of the k and the store typing, the semantic store typing, is our world. Okay. And of course, just like we were making sure, well, just like before, we were making sure that we always appeal to things in the definition at a lower step index. We're doing the same thing. Now, the important thing is editing the definition of type over here. I'll say that psi is drawn from some space that I'll call store type. Psi is a store typing. Okay? So now our type interpretations take a world, which is a pair of a step index and a psi, a store type, and give us sets of values that belong to that type. Okay. And what is a store type? So a type is not cross. Oh, I can't erase that. Let me know if I start writing too small. Store types psi are just a mapping from locations to semantic types, right? And semantic types are these things. So this is just a finite map from loc to type. Yeah? Is there anything wrong with this? Types depend upon store typings, and store typings depend upon types. It's circular. But is it really a problem? Well, let's sort of see if this space could possibly be well defined. We could do a simple cardinality argument. So this equation says that the cardinality of the set type is strictly greater than the cardinality of store type, and this says that the cardinality of store type is greater than or equal to the cardinality of type. Okay, therefore the cardinality of type is strictly greater than the cardinality of type. Okay, so this is a problem. So we need to do something, right? Okay, so what we're going to do is use step indexing to stratify these sets. Okay, so what we want to do is at type level 0, we'll just say type is, think of it as it's just an empty set. All right, and then at type level k plus 1, I'm just trying to express intuition for now, or formalize in a second. At type k plus 1, we only want to depend on store typings from level k. And then we'll say store typings at level k only depend on types at level k. All right, so we've broken the circularity right here by going down a step. All right, now we're good. Yes?
It's the same thing that we do. How many steps of evaluation are left?
Yes, I mean, I could have written n here because right now I was just trying to make an informal argument about the stratification that we are interested in. But yes, it is essentially that. But let's try to formalize it.
Then should we include something like the map that's passed to this? The first
Right,
one,
that's why I was saying that, this case, so when we try to define these sets, we need to be a little bit more careful. So let's call, I'll address the question. Let's call these things a pair of a step index and a store typing. Let's call them worlds. Okay. Maybe we should be putting world above type. I don't have space, so it'll have to go here. So we're going to say that a world at level n is just, let's see, sets, I'll write W, that are a pair of k and psi. Oh, I need to erase this, if that's okay. At least a little bit of it. Okay, so what we're going to say is worlds at level n only contain k's that are strictly smaller than n. I hope you've got this intuition here, because it needs to go. And then we need to say something about this psi. This psi only needs to be, this psi needs to be drawn from this k. So there's a sort of dependency here, right? So we need to say that psi belongs to store type k. And this is precisely what Benjamin was just pointing out. The step index that we use, this psi constrains the level of the psi that's sitting right next to it. Okay, so every time we put this k psi subscript on our type interpretations, we will always assume that if you have a k sitting here, then the psi is drawn from the set store type approximated to level k. Okay? All right. Now, that's my world. What is store type? So now we want to say that type at level n is drawn from world n. So it's a mapping from worlds at level n to these sets of values. And I'll edit the rest of the definition in a second. It's not correct, but let's just get our sort of meta level types right. And we want to say that a store typing, as before, it's a psi is a mapping from finite map from locations to types, but just like I wrote in the equation there, we want store type n to be drawn from type n. Okay, so I've broken the circularity in precisely the way that I was sort of alluding to before, all right? But the actual mechanics of it is right here. A world at level n contains step indices here that are strictly smaller than n. All right? Okay. So everyone good with this? Any questions? Okay, so now let's go back and look at this. What was I trying to do over here? Well, remember we just said that worlds are sort of well-formed. If whenever you have a k here, this psi has to be drawn from store type k. Well, okay, so we start out with a well-formed world. Psi belongs to store type k. We have a k here. But this isn't quite right. The psi still belongs to store type k, but now we have a k minus 1 sitting over here. So we need to do something to approximate, to sort of lower the level of that psi. And I'm going to write that as need to do that there and here. So just making sure that my worlds are well formed throughout the model. All right, and I'll define that approximation in a second. Or maybe I should define it right now. Okay, let's define approximation. So an approximation of any type interpretation, because actually, let's do psi first. Psi approximated to level k is just all the locations that you already had in psi. Psi L is equal to I. Then this is going to be, you just take the range and approximate that. And the way we define approximations of type interpretations is we say that, well, basically we just want to restrict this function to level k. So maybe I don't even need to go to that trouble. I'll just write this as take this function I and restrict it to world at level k. Restriction. So in other words, whatever the function tells you about levels k plus 1 and higher, just ignore that. Okay? All right. Now, let's see. So let's start editing some of these definitions and see what happens. So now everything needs, all type interpretations need to be defined with respect to a world, which is the pair of a step index and a store type drawn from store type k, right? So when do true and false behave like they have type bool? Do they care about what the step index is? Do Booleans care about the step index? Do we care about the store typing? No, right? So it remains exactly as it is. What about functions? What do we do with functions? Remember we were doing this future world thing already? We were saying, okay, if I want to know that a function has type or behaves like it has type tau 1 or tau 2 for k steps, what do? Well, I might apply it either now or at some point in the future. And j, going to a j less than k was a way of going into the future, into a future world. And then in the future world, we wanted some value that behaved like it had type tau 1 in the future world. So we're just going to continue with our world analogy and try lifting this to that. So instead of just going into a future world dictated by steps, right, we now need to say we want to go to a future world that looks like this, j psi prime. And it better be a valid future world, which I'll define in a second, of our current world, k psi. So k psi is our current world. At some point in the future, where this is the world that describes what world, the shape of your store and how many steps you have left, if we are given a value that looks like it has type tau 1 for in world j psi prime, then after beta reduction, we expect to get an expression that looks like it has type tau 2 in the world j psi prime. Right, so everywhere that I had j's, I just put this psi prime. And I need to define this notion of what the valid future worlds are that I can go to. All right, and this is the sort of thing, this is called the accessibility relation for those of you who are familiar with possible worlds models. It describes when you can go from a current world to a future world. What future worlds are valid for us to consider? Okay, yes?
So when you say spell out on the board, that's actually, you're talking about the set of worlds. You're not talking about
this is the set of worlds, just like this is the set of worlds.
elements are worlds in a form where I guess you would enumerate all possible instances of stored typing.
Yes.
Okay.
Okay. So we need to define okay, so what worlds should be valid to go to in the future? So in the future, we have possibly fewer steps left, right? And what might happen to the store typing? If you, the store could grow, right? So between now and in the future, when we have j less than k steps left, we may have done some allocation, right? We may have created some new ref cells. So the store may be larger, which means that the psi may be larger. So we need to allow for that, all right? Okay, so, but we also need to make sure that all of the locations that were in this psi, right? If this psi said that location L1 has to have type tau1, then this psi better say the same thing, because we want type preserving updates, right? We want to keep the same, we want to make sure that locations will always have those types in the future. Okay, so those are basically the things that we need. So we're going to say that j psi prime is a valid future world or of k psi, or j psi prime extends k psi, if j is less than or equal to k, and for all locations in the domain of psi, what should be the case? Right, those locations appear in psi prime, and their types should be the same, right? So this we have to write as psi prime L. Basically, what we want to say is that psi prime L is equal to psi of, to psi of L. But we need to do this sort of thing with the world as well, right? Because ultimately, what we want to do is compare the sets of values in these. So we'll say, do we want to do for all j less than k? No. We'll just say j minus 1 psi prime approximated to j minus 1. This gets a little bit hairy, but you're just basically making sure your world is well formed and going lower a step, is equal to this thing applied to j minus 1 psi approximated to that, right? Okay. Now, what do we have left to do? Well, so this was sort of a straightforward extension, but let's look at expressions now. When does an expression behave like it has type tau? So again, our world is now described by k. Oh, okay.
Psi to psi prime, and how do we choose?
Wait, we're not passing either to either. Wait. So this says, if you ignore this stuff, right?
I'm asking about that stuff.
Oh, you are asking about that stuff. Okay. So basically, you want to take the set psi prime L and compare it to the set, or the function psi prime L, and say that it's equal to the function psi of L at the restriction, at that restricted world, or more approximate world. So we are passing, let's see, psi prime. This is also a prime, it's just gotten, so both of these are primes. Is that basically the question? And, or are you then wondering why that makes sense?
No, I see what.
Yeah, because, I mean, if I started to sort of write W's here, right?
Yeah, this is always the later world that we're interested in.
Exactly.
Psi
Correct.
j minus 1 psi prime.
Yeah. So we'll always use the later world to approximate that, in a sense, right? We don't want to ask the question, we don't want to say that these two contain the same type in the current world. We only care about what happens when we get to the okay? All right. Okay. Psi prime is the later world, right? Or psi prime is part of the later world. This one's later, this one's the current world, and this one's the future world. Sorry? The definition of type n at the very top? Oh, okay, you're right. Thank you. Forgot about that. So I said I would come back to this part of the definition of type n, right? So before, we needed our types to be downward closed. So if a value belongs to the type now, it better belong to the type in the future. Well, let's just edit our notion of future, right? So we need to say for all k, for all k psi j psi prime, such that if j psi prime extends k psi, then if a value belongs to a type interpretation in a current world, then it should belong to the type interpretation in a future world. Okay? So again, just the same downward closed sort of monotonicity property. Extension under future worlds. Okay. All right, how do we determine if expressions behave like they have type tau now? What are we doing with an expression in that definition? We're running it, right? We're evaluating it down to an irreducible. Does this operational semantics, does this even make sense anymore? No, because the form of our operational semantics is on the board behind, but it's, you need to have a store, right, in order to run a program. So we need to have an SE steps to an S prime E and say something about that S prime E prime that we get to being an irreducible state. But how do we pick the store that we want to run with? We need a store that satisfies psi, right? Exactly. So this requires some major space. Okay, so we need to pick a store S such that S satisfies psi, and I'll define this in a second. And we're going to start running this term when we have k steps left. So we want the store to satisfy psi for k steps. Okay? And now when we have this store, we want to say, let's go run E in this store, which should be good, right? Because E satisfies our store typing. If this reduces to a configuration S prime E prime in j steps, where j is less than k, just like before. So we've used up j steps to evaluate to this S prime E prime, which is irreducible. So we can't take any more steps now. Then what should be the case? We want to say the same thing we said before about how E prime should belong to V of tau, right? Okay. But what do we need to say about S prime? So we started out running the term in this world. Running the term may have allocated some stuff, so we may actually have grown our store typing psi. So what we want to say is there exists some psi prime such that in the future, our future is now when we have used up our j steps, right? So in the future, we have k minus j steps left. Psi prime better be a valid extension of the world that we started in, which is k psi. And the store that we've ended up with, which is S prime, better satisfy this new psi prime for the remaining number of steps that we have, which is S minus j. And the value that we got, well, the expression, the irreducible expression that we got, better belong to V of tau for, in the world that we've now ended up with, which is described by k minus j psi prime. Making sense? Kind of making sense? It's the same intuition as before, only now there's this complication of stores. All right? And the intuition really is the same. You want to just run the expression until you get to an irreducible state, and then you want to say that what you got is, behaves like this, like a value form of the type that you wanted, right? We're just doing the same thing. It's just that our notion of worlds is more complicated. So when we go into the future, before we were starting at k, and our future world was described by k minus j when we were done, when we got to that irreducible state. Now we have to start with a store that's good so that we can actually run. We have to say that the store that we end up with is good in some future state, which is a valid extension of our current state, and so on. Right? Okay. So let's define when a store satisfies a store typing for k steps. When do you think that is? Mapping from locations to values, mapping from locations to interpretations of types. So we better make sure that the domains are the same. So the domain of S better be equal to the domain of psi. And what? Exactly. So for all of the locations in the domain of either S or psi, doesn't matter, we want to make sure that the values stored in the store, S of L, look like the thing that psi says they should look like, right? So this is telling us what the type should be, and this is the value. So all of the values in the store better have the type that psi says they should have. Only we're going to need to approximate a little bit, right? So the world needs to be appropriately. So we say that S satisfies psi for k steps if the contents of S satisfy the types in psi for k minus 1 steps, or for all j less than k steps. I'll go with for all j less than k. Sorry, I'll have to put it here. For all j less than k. And then we can just say j and take our psi and approximate it to j. Okay? All right. Yeah?
Could we abstract over the precise definition of world? Like if you just include W for flow?
Absolutely. That's a much better way of writing it. I'm just trying to sort of, yeah. If I were writing this up in a paper, I would write W's here. Okay, everywhere that you have k psi, you can easily write W. You can even define some nice, notation for doing this sort of approximation, so it's not showing up everywhere. In some of the later papers, it's interesting that I use the word later. In some recent papers, people have been using the later operator. So later of I means, or rather later of a world, I should say. So later of a world, where our worlds look like this, right? We take it to mean basically that if k is greater than 0, then later of this world is going to be, how should I say this? Should be, let me just write it like this. Later of that world is k with psi approximated to k. So later means reduce something by 1 step. And you can define a later j as well that, subtracts more, if you like. So just to make things pretty. Okay. All right. Let's put some psi's over here and here. Here, obviously, we don't care for empty substitutions. Here, we need to make sure that we essentially pass around our psi in all the right places, right? So nothing really changes there. We still have this notion of substitutions behaving like, gamma, or values behaving like types in some world, only the world is richer. And then let's talk about how we lift this to open terms. So E behaves like it has type tau under environment gamma. Right? This is the semantic notion of typing. If for all k greater than 0, we pick a substitution. But now we need to pick a psi as well, right? So we need to say for all gamma and psi, such that gamma belongs to G of K psi big gamma, then when you close off the term, you are going to get an expression that behaves like it has type tau in the world described by K psi. So it's something a little bit, so I'm picking a psi, and what am I constraining it with? Basically, I'm picking a set of inputs here, right? Gamma is giving me a set of inputs, a set of values to substitute for all of the free variables in here. We can think of them as our inputs. Some of these inputs may have type ref tau, right? Which means that some of these inputs may be actual locations. Yeah? Okay, so we need to make sure that those locations are appropriately typed, right? Which we'll do over here. And in situations where we are actually, you know, where x maps to some ref tau, we'll go over to that definition, and you know, obviously we need psi to contain some information about those locations. Okay, so basically what we're saying here is your inputs have to be, you know, you're giving me a bunch of inputs. You better also give me a psi that appropriately describes those inputs. Okay, and then we close off our term and we can run it, and psi describes the shape that the store should have before we actually run the term. Okay? All right. So with that done, you then basically want to prove the fundamental property, and type safety follows just like it did before. And it's simply that if B is well typed, then E semantically behaves like it has type tau under gamma. Okay? And that's, again, just by induction on the typing derivation, just like it was before. So I'm not going to go into that. You know, in the appropriate places in the proof, when you, like when you do the proof for new, you will have to extend your store typing. When you do the proof for dereferencing, you'll have to go look in the store typing and say, okay, what does this store typing say about the contents of the store at this location, and so on. Okay? All right. Now let's just talk for a minute or two about what we would need to do to extend this to a binary setting. Like just the most naive thing that you can think of. Like I want to start thinking about, you know, being able to prove equivalence of some programs with references in them. What would change? First of all, I'd have to put pairs of values there, just like we did yesterday, right? And pairs of expressions, just like we did yesterday, right? We'd have that same notion of E1 being related to E2 and a V1 being related to V2. But now these V1s and V2s, let's just look at ref. Okay, so ref would say some L1 is related to some L2 at the type ref tau if something. And how will I know that L1 is related to L2? You have one program that's running. It picks location 100 to allocate at this point. And at roughly the same point, or well, not roughly, at the same point, the other program decides to pick location 200. Right? There's, the order of allocation is not deterministic here. So you can pick you know, location 100 here to correspond to location 200 here. And you somehow in your model, you need to keep track of this sort of thing. So, I don't know, the most naive thing I can think of is to change size so that it doesn't just map a location to a semantic type, it maps pairs of locations to a semantic type. And maybe you could, you know, simplistically say that those locations, there has to be a bijection between them. But bijection causes problems, right? Because surely you want to be able to reason about equivalence of programs that don't allocate exactly the same number of locations. So this is just to give you a hint of the start of all of the problems that start to come up when you reason about state. And it all has to do with, you know, dynamic allocation, keeping track of. So basically, you know, yesterday when we were talking about reasoning about equivalence, we had this relation that we were setting up, right? Now, when you want to talk about the equivalence of two programs that have state, you want to set up relations between their memories, certain invariants that hold forever in the future, right? And you need sort of a lot more, you need very sophisticated worlds in order to do that for a very large, you know, and interesting class of examples. Okay, so I'm going to switch to slides and actually talk about, have references to some of this, and it'll come up again. So I just push that. Okay, so I probably have too many slides, but what we'll do is I'll try to go through parts of it, skip other parts, and then I'll just, we'll put them up on the website and you can look at them for other references. Warming up. Okay, so on the first day when we started, I sort of told you, right? Logical relations, they come in two flavors, unary and binary, right? And I gave you some examples of things that you could prove with unary logical relations. It's up there on the board. And I kept repeating this intuition about, with a unary logical relation, the idea is that a program satisfies a property. If given an input that satisfies the property, you get outputs that satisfy the property. Right? And then when we move to binary logical relations, again, just examples of things we can prove with binary logical relations, the intuition becomes if you give me related inputs, I give you related outputs. Right? If you remember anything from these lectures, remember that. Okay? All right, and we've talked about some of these things. Andrew's been talking about non-interference, and you can use binary logical relations for proving compiler correctness. And I'll come back to this because I have a slide about some current work on this. But here the basic idea would be to set up a logical relation between a high-level language and the low-level language that you're compiling to. Okay, so history first. So someone was asking me, that could I talk about sort of history, and so here it is. So I think the earliest instance of logical relation is in '67. That was Tate's method. They were not called logical relations at the time. So, so this is still referred to as Tate's method, proving strong normalization for simply typed lambda calculus. And then Girard in '72 proved strong normalization for system F. This is the so-called reducibility candidates method. This is, also an instance of logical relations. Then Plotkin in '73, and this is an unpublished thing. I think it's just a tech report, probably Edinburgh Tech Report. Lambda definability and logical relations. Plotkin was the first one to use the term logical relation. And if you want to Google it, it's sort of interesting. Google types mailing list, Plotkin logical relations, all right? There's a post back in '89 or something where Plotkin tried to explain why he was using the term, et cetera. And there's been discussion like every 10 years or so, someone again asks, why are logical relations called logical relations, and who coined the term? So it's interesting. Okay, Statman 85 is another very early reference. Here are two papers that you absolutely must know about and read, I think. Okay, so Reynolds in '83 had his famous paper, Types, Abstraction, and Parametric Polymorphism. So this is where he used logical relations and formalized this notion of parametricity. What type abstraction actually gives us. And then Mitchell in '86. So before '86, there's an '85 paper by Mitchell and Plotkin. Right? Yes. Okay. By Mitchell and Plotkin called Abstract Data Types Have Existential Types. So in '85, Mitchell and Plotkin realized that the thing that we call abstract data types are really just an instance of existential types. Andrew sort of alluded to this at some point in his first lecture. He said, we want mechanisms for, what are good mechanisms for encapsulation, or something to that effect. And then he put up modules up there, and he put up classes / objects, and he said, well, these are all just instances of existential types. And abstract data types are just instances of existential types, which, existential types, you sort of see them uniformly appear as, a core mechanism of abstraction. All right, and then Mitchell's paper formalizes, just like we have parametricity, the property of parametricity for universal types, for polymorphism, representation independence is the dual notion for existential types. It says that no matter what concrete implement, no matter what concrete type you use to implement your interface, right? The client of and the interface of that abstraction of that ADT won't be able to tell the difference. Okay? Concept of representation independence. All right, and then there were lots of uses in the 80s and 90s, but so this is where my subjective sort of opinion perhaps comes in. Around 2000, I would say that there had been quite a few papers on logical relations. But until then, logical relations were sort of primarily done in a denotational style. Actually, that's not completely true, because Andrew Pitts was doing logical relations in an operational style, right? I've talked about denotational versus operational before. Denotational is where you define the interpretations of types using some mathematical objects, right? And operational is the kind of stuff that we've been doing. You want to know if an expression behaves like it has this type, run it. If you want to know if two expressions are equivalent, run them and see if they give you related values, that sort of notion. Okay, but the denotational semantics, comes with rather complicated math. So basically what happened is that, people who really had it in them to go and do this would do this. But for the most part, everyone sort of viewed logical relations as this beautiful, elegant proof technique, but only used it for simply typed lambda calculus and system F, essentially for mostly in terminating settings. And I'm grossly generalizing. There are lots of instances of this not happening, but overall, I think that people, used it in a sort of toy and idealized setting. And the main problem was how do we handle recursive types, which you need for lists and objects? How do we handle mutable references that can store objects, that can store functions? So higher order state is a term used to refer to this notion, where you can have a mutable reference that stores functions, first-class functions. So, that's sort of the main contribution of step index logical relations, that it allows you to model references in much the way that I've shown you today. You could just easily throw in universal types and existential types, and it wouldn't look any different than, what we were doing yesterday without references. The intuitions carry through. The intuitions scale, basically. That, in my opinion, is the biggest thing about this method. You don't have to go and sort of reinvent the mathematical machinery when you add a feature that doesn't operate well. And around 2000, there was a lot of work on type-preserving compilation first, and then proof-carrying code. And around 2000 and in the early 2000s, people started to talk about the fact that, well, we're programming languages people. We should mechanize our proofs. Benjamin's been a huge part of this, and you guys have been doing this, right? So one of the problems with those denotational logical relations is that they're really hard to mechanize, because you have to mechanize a lot of mathematics, a lot of it, before you can, even start doing interesting things. And the nice thing about step index logical relations is that the stuff that you're mechanizing, it may be tedious, the steps and so on, but it's much easier to sort of get to a complete definition, formalized and mechanized. Okay, so here's sort of a comparison slide that I've had from another talk. So, but what I want to point out here is the references that are in black. All right, so this is my review of not all the papers written during this time period, but sort of some highlights. And I want you to focus on, when were we able to handle existential types and universal types together with recursive types and references. And this was sort of missing. The stuff in black are denotational models. The stuff in blue are operational logical relations. And by the way, except for the Tate-Girard reference at the top, all of the stuff after that is binary logical relations. I intentionally left out lots of good unary stuff, but they're all binary. So the stuff in blue are operational logical relations, but not step indexed, and the stuff in red are step indexed logical relations. Okay, so what are the highlights here? Let me just sort of point out highlights. So a highlight for, this doesn't show up at all. You're supposed to see shading at this point, but you can't see any shading. Okay, so the black stuff, I would say, is generally, like Boer-Burke et al., Benton Leprosy. This stuff is pretty complicated denotational semantics. They were able to handle recursive types and references. Here they were able to handle recursive types and references, but only references. You could have a ref of int, but you couldn't have cycles in the store, because that would have required more complicated mathematics. So this was the sort of stuff that people did. You know, they cut down the space of the features that they had to model, or the language that they had to model, so that it wouldn't get super complicated. The work by Pitts and Stark is really, really nice. 93, 98. They decided to say, okay, fine, we don't care about storing functions in the heap, but you know, we're just going to talk about references to integers, the most basic thing. But they made a lot of progress on reasoning about interesting examples where, you know, you have one program allocate more locations than the other, and there's this notion called local state, which I don't have time to explain, but it's when some locations are caught up inside a function closure, so therefore they're hidden from the client or the context, and this makes reasoning about equivalence tricky. Okay, let's move on. Okay, so step index logical relations started with Appel McAllister in 2001. And if you want to read the story about it, I'll tell you the story about it. Okay, so this happened in the context of the foundational proof-carrying code project, which was going on at Princeton. And the foundational part of this PCC project was that Andrew Appel said, we are going to you know, do proof-carrying code, but with the smallest trusted computing base possible. So until then, George Nekula had an instance of proof-carrying code where he had, you know, his low-level typed, let's just call it a low-level typed machine language, even though that's a slight mischaracterization. But you know, if you think about, okay, or let's think about it as typed assembly language. Once you get to the assembly language level, you have a lot of instructions, a lot of rules, and you have a type system. This is what Greg Morissette and his students did. Right? They showed us how to do typed assembly languages. But we didn't have mechanized proofs of that typed assembly language. Right? And there was actually a proof-carrying code system for Java where there was a bug in one of these rules, because there are a lot of rules when you get to that low level, and they're much harder to understand than these simple baby calculi that we play with. Right? So having mechanized proofs there is really a nice thing. So in the context of FPCC, we wanted to prove type safety at the machine language level. Have a mechanized type soundness proof, trusting only a couple of hundred lines of higher order logic, and you know, some bits of the runtime and so on. Okay, but we were stuck. How do you? We were using. We didn't want to use progress preservation to prove type safety, because at the time the only you could use 12 at the time to do proofs of progress preservation, but 12 wasn't quite mature. You know, I mean, now it's way better, but Andrew's argument at the time was, well, you would need to trust the schema checking and the cover checking and so on. That's all built into 12 in order to, you know, essentially check proofs of progress preservation. I'll leave it at that. So the idea was, how can we just, you know, trust the axioms of higher order logic and do this proof from the bottom up? And that's the style of type safety proof that I've shown you. That's exactly what we've done. But the problem was that we didn't know how to handle recursive types. But anyway, there's a lot more history there. If you're interested, I can point you to references which actually have stories about this. But Andrew sat on a bus with Dave McAllister at CADE 2000 on the way back from a whitewater rafting trip. Sorry, this is irrelevant trivia, but it's interesting. And they happened to talk about this, and Andrew was like, you know, at the time he was trying to formalize a whole bunch of mathematics from John Mitchell had a student, Mahesh Viswanathan, who had formalized this stuff, and he thought we would use that sort of semantics to do this type safety proof, but it was way too much. It's like you're formalizing a lot of stuff about basic computability in order to even get to the interesting bit. So McAllister pointed out that you could adapt ideas from the infinity models. That rings a bell for anyone. Anyway, so that led to this sort of step index logical relation idea. The initial paper was just recursive types. My thesis extended it to type safety for references, recursive types, and polymorphism. This paper did what I showed you yesterday. I was pointing you to an ESOP 06 tech report. So that's what this was. And then in 2009, with Derek Dreyer and Andreas Rosberg, we had this, and by the way, I stopped at 2009. We did a logical relation which you could use to prove prove equivalence of lots of really sophisticated and interesting examples in the presence of state and polymorphism. Okay, I'm not going to go through any of this. Let's see how much I have time for. I've already said stuff about foundational proof-carrying code. So this slide has a bunch of instances of unary step index logical relations. All right, so using them to prove type safety. FPCC did this for all the things that I just mentioned, and the main thing here was that we built a model of a low-level typed assembly language, all right, which was the target language of a compiler for core ML. And then if you're interested in substructural types, linear types, and so on, you can look at some of these references. Work that Matthew Fluid and Greg Morissette and I did on doing type safety in the presence of, when you have linearity and affine types and so on. And for those of you interested in objects, Jan Schwinghammer and Kaplan, is that how you pronounce it? Catalin have this paper where they do type safety for Abadi-Cardell's imperative object calculus, which is very nice, and it sort of gives a more relaxed sort of formulation of some of the things from my thesis in an object setting. I was telling someone about this yesterday. Okay. Andrew Appel and Aquinas Habor and Francesco Zappanardelli have used this in the setting of CompCert. So they so they proved the soundness of a concurrent separation logic with respect to this concurrent C minor operational semantics. And the whole point of this was to come up with the semantics to adapt Xavier's CompCert proofs to a concurrent setting. Let's switch to binary logical relations. So I've already talked about some of this. A very nice paper. So I mentioned this Popolo 9 paper with Derek Dreyer and Andreas Rosberg, which was the first to do this, state plus type abstraction kind of thing. But there's a follow-up paper. Derek Dreyer and Lars Berkedal and Georg Neis, as far as higher order state is concerned, or mutable references that can store functions, etc., are concerned, this paper isn't more powerful, but it's more elegant. So they took all of the initial ideas that we had in that Popolo 9 paper and made it sort of more beautiful. And they have this notion of state transition systems. So the worlds, I said to you that the worlds need to be more complicated to express interesting relations between the states of your two programs. And these state transition systems allow you to sort of write down a protocol that you expect to hold in the, as you go into the future, as you run your program at a high level. Okay, I'm not going to talk about this. One thing I should mention. There was a paper that, how do I say this? I have used step index logical relations in a setting where there were no types. That's a very important thing to be aware of. If you want a reference, it's this Popolo 8 paper of mine. But never mind that, it doesn't matter. The important bit here is that once you start to do, once your induction is defined using steps, right, using the K, you don't really need to do induction on types anymore. Until then, or until step index logical relations, you couldn't, everyone always said, but logical relations can only be used in a typed language. This was a comment that was pervasive. And it's not true anymore, and it's good to be aware of that. So if you need to use this sort of technique to break circularities, just do induction on the steps and forget about types. You don't need them. I'm going to talk about this work. Yes, compiler correctness, since Xavier is talking about compiler correctness. So I've said that you can, okay, let me start out with an observation. Maybe Xavier has pointed it out already. In CompCert, the compiler, the theorem that you prove, that compilation is semantics preserving, applies only to whole programs. Okay? So if you compile, a program component, a module, something, down to assembly, and then you link it with some library code, maybe some runtime libraries or something else, or maybe you wrote some components in another language and compiled them down to assembly. You want to link with those. At that point, if you're linking with code that was not compiled by CompCert, then you don't have any guarantees of compiler correctness, formally speaking. Okay, and I think this is a fascinating open problem, a really, really important one. Nick Benton has put forward a really, has put forward one way of doing compiler correctness for so-called open programs, programs that are not whole programs. He calls it compositional compiler correctness. I don't like the term so much, so I just wrote open programs. And the idea, as I've been saying, is to set up a logical relation between source and target. This logical relation acts as the specification of the relationship that you want between, high-level code and low-level code. When does a piece of low-level code correctly realize a piece of high-level code? Benton and Her have done this for, System F down to an SECD machine. So they've shown compiler correctness. And Her and Dreyer have extended that to a source language with mutable references. But what they do is they set up this logical relation between source and target. The technique doesn't work right now in the context of multi-pass compilers. You have to set up one logical relation between the absolute source and the absolute target. So you can't implement your compiler the way we normally implement compilers in multiple passes. Okay? And this has to do with this weakness they're using step-index logical relations. This has to do with proving transitivity. You have one logical relation set up that relates source language to intermediate language I, and another one that relates intermediate language I to target language T. And now you need to say that now that you've proved these two things, right, your first compiler pass and your second compiler pass are correct, you want to conclude that your full compiler is correct. Don't have that property. Okay? Now, that's one problem. The other problem is more subtle. So here's the theorem that you actually prove. You prove that if you have a source language, a source program little s of type big S, and it compiles to some target T, then the theorem that you're proving is that S is related to T. And the big S that we put over there is the type of the source, not the target. But anyway. Now, the consequence of this, the reason this can handle open programs, is this bullet here. If you have, so let's take a look at what happens with the function rule, right? If you have a source program that's a function, s prime to s, and you are given an s prime, then if you know that s is related to t, and s prime is related to t prime, then just by the definition of logical relations and how they're set up, you immediately have that s applied to s prime is related to t applied to t prime. This is the notion of composition. This is how you can take an arbitrary t prime and hook it up with your t. So you compiled s to t using CompCert or your certified compiler, and now you are given a t prime. So notice if I use my verified compiler to compile s to t, if I now want to link with t prime, what do I need to do? Based on the bullet that I put up here. If I want to reason about linking with t prime, I need to write down an s prime that is related to that t prime first, right? This is not good, right? Because someone could give me some piece of target code to link with that's like a few hundred lines of assembly, and I wouldn't be able to decompile it to figure out an s prime, right? So this is, I think there's still a lot of work to be done here. Does that make sense to people? Do people want to talk about it? Okay, I'm really interested in this problem right now. So, okay, Benjamin has used binary step-index logical relations in the context of differential privacy. There's a very nice ICFP 10 paper, and I think this is still ongoing work that Marco is doing with Benjamin. And most recently, we have just written a paper about a logical relation that you can use for reasoning about equivalence of fine-grained concurrent data structures, and we can handle many, many sophisticated examples, so it's kind of cool. Very complicated, though. Okay, I am not going to go into various things. There's been a lot of work on hiding the steps. Okay, you can do this in two ways. I'll mention this one. You can sort of build a relational logic on top of the step-index logical relation and essentially hide all the steps, except in a few places you'll have this later modality, and those places will mark where you need to go down a step. That way you don't have to, you can use the logic to prove equivalence of programs and not have to worry about the, turning the crank with the logical relation itself. So this makes the proof method easier to use. This work in direction theory makes these logical relations easier to mechanize. Okay? So if you're interested in mechanizing this stuff in Coq, go look this up. Hobart, Dawkins, and Appel, Popple 10. I should stop. Let's see. Okay. Yeah, let's stop there. You guys can look at the slides, and there are references there, and if you find some of them interesting, just pull them up. Okay, thanks a lot.